Okay, so 2-4, now we're looking at compound interest and the number E here, okay? And we're going to introduce to you that value. Let's start there. Have we seen the number E before? Yeah? Some of us? Okay. So, well, if you haven't seen it before, the number E's given by the expression 1 plus 1 over n to the power of n as n gets infinitely large, as n approaches infinity. So basically what we mean by that is if we plug an infinitely large value in for n within this formula, there's going to be a numerical value that expression takes on, okay? And we want to see what that value ends up being, all right? So you could represent this with limit notation. Limits are something we're going to study later on in this course, and then you study them again in calculus. But basically, this would be what the limit notation looks like. You'd say the limit as... You good?
No, it's so wet.
Oh, boy.
It's so bad.
The limit as n approaches infinity of 1 plus 1 over n to the power of n. So that's just a fancy way of saying I want to make n as large as I can and see what the value of this takes on. All right? So I'm going to pull out my calculator and I'm going to plug in some different values for n. Maybe. Okay, so let's just start with what if n were 1? 1 plus 1 over 1 to the power of 1 is going to yield 2. So that tells me the number E is somewhere along the value of 2. Okay, well, let's increase that value of n. Let's make it a 10. Okay, now we took a pretty big jump there. We went from 2 to 2.59. Let me keep increasing this value of n until I get the same decimal out to 3 places, okay? So let's go 100, okay, 2.704, about 1,000, 2.716, all right, so at least I'm to the 10th place. We know it's about 2.7, okay, 10,000, 2.718, about 100,000, 2.718. So there you go. Tells me E is approximately to 3 decimals a value of 2.718. Okay, now your calculator is programmed with E. So if you have your calculator with you, you can pull it out. To access it on the scientifics, you probably are going to need to hit the second button, followed by your LN button, which is your natural log button. Okay, now if you do that, what does it give you? It gives you E and makes you do what?
E here, parentheses.
Yeah, it makes you put a power on it, right? So if I just want the value of E, I make the power 1, and it should give you its true value. Okay, so I go back here. Mine's slightly different. I just hit E, raised to the first power. There you go, 2.718, 2818, 28. You guys getting something similar? Should. All right, so we make a big deal about E. It shows up in a lot of applications, okay? We're going to see a little bit of it later in this lesson, and then some more involving logarithms later on, all right? You could make E, it's a real number, so you can make it the base of an exponential function. So here I have f of x equals e to the power of x. I call that the natural exponential function, okay? And notice it's very similar to the graph of y equals 2 to the power of x, right? Again, I refer to it as the natural exponential function. It's kind of like if you're watching Monday Night Football, they put the rosters up on the screen of the players. They always say what college they played at, right? When you get to somebody who played for the Buckeyes, what do they say? I went to the Ohio State University, right? They stress the in that name. Okay, same idea here. All right, go to example 1. We got $5,000 deposited into an account offering 8% annual interest compounded quarterly. How much will be in the account after the following number of years? We're going to use this example to help us develop or derive our compound interest formula, okay? So we have this 8% annual interest, and we're compounding the interest quarterly. That means how many times in 1 year? 4 times, right? So that 8% is being divided over 4 times in the year, and that's going to give me 2%. Okay? So let's calculate how much we'd have after the first compound, which would be 3 months after we deposit this money. So that's going to be 5,000 times, added with 2% times 5,000, right? Now there's a common factor of 5,000 that I can pull out here. Okay, and I could call that 5,000 times 1.2. 1.02, excuse me. Okay, now after 6 months, I've got to take the amount that's in the account after 3 months, and I got to add to that 2% of it. Let's use brackets here. Okay, so now there's the GCF of 5,000 times 1.02. I've pulled that out. And what am I left with? 1 plus 0.02, which I can simplify this now to 5,000 times 1.02 squared. Okay, now what's it going to be after 9 months? Well, I take the 5,000 times 1.02 squared. That's how much was in after 6 months. And I have to add to it 2% of that value. So I can now factor out 5,000 times 1.02 squared. And that would leave me with 1 plus 0.02. So this is 5,000 times 1.02 cubed. And I can continue this process, right? So what is it going to be after 12 months in the fourth compound? 5,000 times 1.02 to the power of 4. Everybody okay with that? All right. So now let's try to generalize this so that it'll work not just for this 1 year, but for multiple years. Okay. So I'm going to build a function a of t. It's going to start with our 5,000. And then here's how I'm going to think of this. The 1.02, we got the 0.02 of that by adding to 1 our original annual interest rate divided by the number of compounds, 4, right? And then instead of just raising this to the power of 4, we need this to work for any number of years. It's now going to be raised to the power of 4t. Everybody okay with that? All right, so now how much would be in the account after 7 years? I just got to find this function evaluated at 7. Okay, and let's pull out the calculator, see what we get. 5,000 times 1 plus 0.08 divided by 4. Of course, you could put that in as 1.02. Raised to the power, I'm just going to say 4 times 7, I know is a power of 28. So it's going to be worth $8,705.12 after 7 years. Questions there? Okay, so what we just came up with for A of t, we can generalize that for any compound interest scenario, okay? And I have that formula on the next page, example 2. So our compound interest formula is A of t equals P times 1 plus R over N to the power of N times T. So P is the same as before, R, our interest rate expressed as a decimal. N is the number of times we're compounding. And then T is still our time in years. Okay? All right, so let's say now we're taking $34,000, depositing it into an account offering a 5% annual interest rate. What's going to be in the account after 4 years if we compound it semi-annually? What would N be in that case? Semi-annually. 2. Okay, so I would say the amount after 4 years, A of 4, would equal my initial amount or my initial principal of $3,400 times 1 plus the annual interest rate of 5%, 0.05, divided by 2 to the power of 2 times 4. Okay, so that's going to be 3,400 times 1.025 to the power of 8. And that would approximate out to $4,142.56. All right, what if I compounded monthly? What would that make N? 12, right? So A of 4, the amount after 4 years in this scenario, would be 3,400 times 1 plus 0.5 divided by 12 now to the power of 12 times 4. Okay, now if you try to simplify what's in the parentheses there, this time you should end up with a repeating decimal. Okay, and then ultimately that's going to simplify to $4,151.04. Notice you're gaining more interest with more compounds, right? Okay, questions there? All right, example 3. Imagine a bank would allow you to compound an infinite number of times instantaneously. So the moment you have some interest calculated, you can earn more interest on that new amount in a moment's time. Okay? That is known as continuously compounded interest. Okay? Now, it's not really a thing. No bank is actually going to allow you to have an infinite number of compounds. But it's a good concept to look at because it tells you, if nothing else, it tells you what's the maximum amount you can make in an investment scenario. Okay? And here's where we see E come into play. We have a special formula for continuously compounded interest. It's A of t equals our principal P times E raised to the power of RT. I like to call this the shampoo formula because the letters are P-E-R-T. That spells PERT. PERT is a shampoo. I don't know if that's still around, but when I was growing up, Pert Plus was a pretty popular shampoo. Okay, so anytime I see the word continuously compounded, I'm using the shampoo formula. I'm using Pert. Okay? All right, so let's say same scenario as before, but now we're compounding it continuously. So I know to use the formula up above. So it would be A of 4 equals 3,400 for my principal times e to the power of 0.05 times 4. And from there, it is calculator work.
Pardon this interruption. Girls' soccer practice is canceled today due to the weather. Thanks. Have a great evening and stay dry.
All right, now be careful when you put this into your calculator and you raise to the power. If you're not actually going to multiply out the 0.05 times 4, make sure you put that all in parentheses. Okay, $4,152.77. So think of it, that is the maximum amount this account could be worth at the end of 4 years. You could not exceed that value. Okay.